Okay. All right. Today, we are going to take a look at k-nearest neighbors, which is a classification method. And so k-nearest neighbors is what we call a non-parametric instance-based learning method. And so unlike other models like linear regression, where you're learning a set of parameters like the slope and the intercept from the training data, instance-based models simply just store the entire training data set. And the way it works is it classifies new observations by identifying the k-nearest points in the training set and assigning the new point to the class that is most common among these neighbors. So the process looks kind of something like this, where the very first step is you're going to compute distances from the test case to every single data point in the training set. Okay. And so if you have a big training set, this can be a very computationally expensive step. Once you've computed distances to every single point, then you are going to pick the k nearest of those points. And that's how we get the name the k nearest neighbors. And then each of those points that are the nearest, um, each get a vote, and we use majority voting among those k neighbors to determine the class. Now, there's a few important considerations that you need to think about when using k nearest neighbors. And number one is that you want to use k nearest neighbors if you only have numeric variables, numeric features. And so because k nearest neighbors uses distance metrics where you're measuring distances, that's going to work really only for numeric variables. If you have categorical variables, it is possible to code them into zeros and ones, but but it's just not going to work as well. And there's a lot of questions on whether it's accurate to encode these things as zeros and ones, because everything that's a yes gets encoded as a one. And what is that distance, and what exactly does that distance represent? And that's a challenge. So really, it works best for numeric features only. Okay. The other thing that you want to do is you want to scale all of your features to be on a similar range. So, an issue is that if you have one of your variables, one of your features has a much bigger numeric range than any of the others, it can really dominate the distance calculation, and then that would reduce kind of the influence of the other features. So, for example, if you had like income as one of your predictor variables, you might have, one person's income might be, $30,000, and another person's income might be, 200,000, and you have a difference of, 170,000. Versus if you have age, okay, maybe perhaps the youngest person in your data set might be 18, and the oldest person in your data set might be 100 years old, but that's only going to be a distance difference of 82. And so because you're using distance metrics, that distance of $170,000 is going to just be much, 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 much greater. And so that's really going to kind of distort, the relationships, and ultimately degrade prediction performance. So a common approach is standardization. So basically making everything z-scores. So you're going to have a mean of 0 and standard deviation 1. I mean, if you have something really skewed, you might want to do some kind of transform, like a log transform. I didn't mention that in the slide, but the idea of scaling is important. The other is min-max scaling, and that's basically going to just kind of you subtract the minimum value from everything, and then you divide by the range. And so basically your smallest value will become 0 and your largest value becomes a 1. These are just some ideas that you can use as far as scaling. Okay. Another thing that you have to consider is what value of k, how many neighbors should I use in my model? Um, if you choose a small k, what ends up happening is your model ends up being super flexible, and it's going to capture any kind of patterns, local patterns, very closely, but you run the risk of overfitting your data. Okay. And then the other issue here, so you're going to have low bias there, but the other issue is you're going to have a very high variance, and it's going to be very sensitive to noise and any kind of weird specific instances that are in your training data. Okay. And so if you grab another random sample, it might end up with very different predictions. Okay. On the other hand, if you pick a large K, okay, then your model is going to have high bias. It's not going to be as flexible. It's going to really smooth out any kind of local variations by basically averaging over a larger quote neighborhood by taking into consideration more data points, a larger K. But you'll have a lower variance in that your predictions are just going to be a lot more stable across different subsets of your training data. So even if you pick a different random sample or things like that, you'll have it won't your predictions won't change very much. Okay. It'll be less affected by individual noisy data points, but you run the risk of underfitting. Okay. And so how you pick your K, whether you want a large one or a small one, you'll probably decide using cross validation, and you'll kind of through a process of trial and error, you will attempt different sizes of K, and you'll measure its prediction performance. Sometimes with K nearest neighbors, because when you do your classification, there's a majority vote at the end. Sometimes there's a tie. Okay. Now you can kind of avoid this a little bit if you have only two classes and you keep K to be odd. Okay. But if K is even, or if you have more than two classes, then it's possible to have a situation where you have a tie, even among your K nearest neighbors. And there's no, set rule on how ties should be resolved. And so here's a few different strategies or ideas. Okay. And one is you just say, hey, this data point, we don't know how to classify, and you just leave it as unclassified. Okay. And then another is you just select randomly among the tied groups, the top tied groups there. Another idea is you do weighted voting. And so not just if you have the six nearest neighbors, okay, and it's split 3-3, what you do is you say each of these votes gets a different weight. The ones that are closest, their votes count more. The ones that are farther away, their votes count less. And if you do that, then you're less likely to have a tie. Even if it's split 3-3, it's probably three of those votes will have a higher weight than another three. Okay. You can also just switch to the one nearest neighbor and say, okay, well, it's a tie, it's tie 3 versus 3. But if we look at the nearest neighbor, then it's going to be, class A. Okay. Or among the top tied groups, you can also select the group with the closest neighbor. That's not necessarily the same as picking the one nearest neighbor. A lot of times it yields the same results, but it's not always exactly the same. One of the kind of biggest drawbacks of using K nearest neighbors is that it is computationally very expensive. And so if you have n training data points, and each of those n data points exist in d dimensions, okay, then calculating the distance from your test point to all n training data points is on the order of n times d. Okay, this operation gets bigger and bigger and bigger as n grows or as d grows. Okay, you also have to sort all of the distances, and that also grows as n gets bigger. Okay, the majority voting, that doesn't really grow. But you can see that if n is really big, okay, or also if d is really big, then k nearest neighbors is going to be, computationally expensive. There's a few other methods. I'm not going to really get into it, but there is something called the KD tree, and that should, speed up neighbor searches. But that only works if your number of dimensions isn't too big. Okay. Um, and if you have really high dimensional data, even that's not going to really help. K nearest neighbors is generally considered to be what we call a hard classifier because after you do the majority vote, it just assigns the class label among the most frequent among those K nearest neighbors, and this is just going to be a categorical designation. But you can extend K nearest neighbors to provide, say probabilistic outputs. And this is done by like saying what proportion of neighbors belong to that class. So for example, if you had K equal to 5 and 3 of the neighbors are class A and 2 of the neighbors are class B, you might say, okay, this is going to be class A with a 3/5 or 60% quote unquote probability. But these are not real probabilities. They're just kind of observed relative frequencies. But they can still be useful as far as understanding, how confident we are in the prediction. So if it is kind of split, like 3 out of 5, then we'll say, well, it wouldn't be as surprising if it turned out to be class B. Okay. Whereas, if you're in a kind of a region where all 5 are class A, it's 5 out of 5 class A, then, it would be a lot more surprising if it turned out that the test case was class B. Okay. As far as measuring our distance to determine which points are the closest, we typically use Euclidean distance. Okay. But there are other ways for us to measure distance. And so we have Manhattan distance or taxi cab distance. Basically, you take the absolute values of the differences of your coordinates and then you add them up. And this is perhaps favored if you have heavy-tailed distributions. There's also the Chebyshev distance, and that is found by kind of taking the maximum absolute difference between any like coordinate of 2 points. So you look at your x coordinates and your y coordinates and your z or whatever it might be, and you just do the maximum of the absolute. So it's a measure of like taking whichever feature is the most different, how big is that difference? And then another is cosine similarity. You measure the angle between vectors, okay, and you ignore the actual magnitude. This is a little bit more popular in, say, like text analysis, because in text analysis, you might have documents where there's vastly different word counts, and so the relative the relative proportions of word frequencies is more important than the absolute counts. So it'll be something like, the word president is the most common word in this document, or in both documents, the word president is the most common word, but if you did absolute counts, the absolute counts are drastically different because, one document might have been 10 times longer than the other document. Okay. Some advantages about k-nearest neighbors is that it's very simple, straightforward to implement. And another advantage is that it's non-parametric, and so we're not making any assumptions about the underlying data or distributions. Okay. And then there's also no training phase. Okay. As far as it goes, as soon as you're ready to make a prediction, you can just perform the classification with the test case. No need for training your model. Okay. But there's a lot of disadvantages in that it is very computationally expensive, especially if you have large data sets. Okay. And then also because you are storing the entire data set, it requires a lot of memory on your computer. Okay. Um, it also doesn't learn any kind of rule or function. It just relies solely on comparing the test case with existing data. So if you're looking for like, okay, can we generalize this to something larger or, learn some kind of rule, you're not going to get that. Okay. High dimensional data also causes more problems. Choosing what value of K isn't necessarily straightforward and requires kind of a lot of times trial and error to figure this out. Okay. It's also sensitive to outliers because your distance measures can be skewed by extreme points. And if you have anything with kind of missing values, you're not going to be able to use that in your training data, or you're not going to be able to figure out the classification if it's in your test data. Okay. And then another problem is that if you have one class that is just much more frequent than the other, right? If you have like a severe class imbalance, then k-nearest neighbors could end up just predicting the majority class for like almost every single one of your data points, which is probably not what you want. Okay. All right. The next series of slides will just show you examples of how k-nearest neighbors would work. Okay. So here is just some pretend training data. All right. I've got two classes, dots in red, dots in blue. And then I'm going to pretend that we put in a test case right here at this location, 0, -1. And so the very first thing we are going to do is we are going to measure the distance from that point to every single other point in the data set. And so that's represented by these lines from the test case to all of our training data. And then we will pick the nearest neighbors. Okay. So here, if I choose k = 1, the one point that is closest, the one with the shortest distance, is this red point right here. And so to kind of show that it is the nearest neighbor, I've drawn a circle to show you that no other point is closer than that. And so in this case, we will use this is the only point that gets a vote, and it votes red. And so we will predict this test case is red. Okay. I'm going to go up to k = 3. And at k = 3, these are our three nearest neighbors. We have one blue and two red. And so as far as the vote goes, it's 2 to red to 1 blue. And so we are going to predict red. If I go up to k = 5, these are the 5 nearest data points. And now when we vote, okay, these 3 points vote blue, these 2 points vote red. And so with the 5 nearest neighbors, our test case will get voted as blue. Okay. At k = 7, these are the 7 nearest points. This point is really close, but after drawing the circle, apparently it's a little farther away than this red point. So we have 4 blue and 3 red. And so using majority vote, the test case would get voted to be blue. And so, so in this case, depending on what size k, so k = 1 and k = 3, it gets voted as red. For a k = 5 and k = 7, it gets voted as blue. So what size k you use would change what kind of prediction or what kind of class you would predict. Okay. Here is another test case. This test case is located at 1, 1, and we'll just see how k-nearest neighbors would classify this point. All right. And so again, the first thing we do is we measure the distance from our test case to every single other data point in our data set. And then if we look at the one nearest neighbor, it would get voted as red. If we look at our three nearest neighbors, we have two red and one blue, so it still gets voted as red. With five nearest neighbors, we have three red and two blue, so it still gets voted as red. And with seven, we have four red and three blue, and so it still gets voted as red. So, for this test case, it's kind of more consistent. Like it always gets voted as red. And so this kind of reflects that, this test point is, more solidly in the kind of quote um, red region of the of our graph. And that I think that aligns with what we are seeing here. We can kind of this is just a bunch of code that can kind of draw a decision boundary. I'm using code from the Stack Exchange post, right? Where basically the way the boundaries are drawn is that we take our data, and you can see all of these tiny little dots here. And basically, I performed k nearest neighbors with k equal to 1 for every single dot. And I said, okay, if I have a dot right here, what is my nearest neighbor? All right, and it's blue. Okay. If I put a dot right over here, though, and I say, hey, what's my one nearest neighbor? It ends up being red. And so this ends up being the border boundary between kind of the blue and the red regions of our data. Okay. And so you can kind of see like here I have a red dot and a blue dot, and the boundary kind of gets drawn as like, what's equidistant from the red and the blue. And so all the dots on this side of the boundary are a little bit closer to the blue dot. All of the dots on this side of the boundary are a little bit closer to the red dot. And so this is the region here. Okay. And I repeated this process where, we have this grid of points, and for every single point in the grid, I just said, hey, what are my three nearest neighbors? And depending on the three nearest neighbors, how would you classify each dot? And this is the resulting boundary that we see. And here it is for k equal to 5. And here it is for k equal to 7. And, as the k increases, it doesn't, it's a little bit hard to see here, but the boundary gets a little, quote, more smooth-ish, okay? And, it doesn't quite look like it's very smooth here, but basically we're taking into account more points for every single one of these things. We're taking into account to more neighbors, and so it is less affected by kind of local variation. So for example, with k equal to 1, this one red point, which kind of seems out of place, uh, greatly influences where the boundary is when k equal to 1. Okay. Kind of the prevalence is the effect of choosing k is a little bit more noticeable when you have a lot more data points. So here I have a bunch of red points and a bunch of blue points. And so, the overall boundary is kind of red dominates the right-hand side and blue dominates the left-hand side. Although we do have kind of, a sprinkling of red points over here and a couple blue points over on this side. And so when you have something like k equal to 1, with k equal to 1, every single data point exerts influence over its kind of immediate neighborhood, right? So this one red data point kind of influences its immediate neighborhood. And so this, we have these little exclaves of red over here, and this blue dot influences, has influence over its immediate neighborhood, and you have this kind of very jagged boundary. But as we increase the the k, so here it is with k equal to 3, now we start to kind of average over, more data points. So there's a few kind of, oddities here. This this region right here, the three nearest neighbors are actually these blue dots, and so you kind of get this small little pocket of blue, in this region of red, and then you have these two dots that are red, and so whenever you say k equal to 3, any dot in this kind of neighborhood, the three nearest neighbors are two red and one blue, and so that's what we have there. Okay, but again, as k grows, the boundary, okay, and again, smoother is a little bit of a weird word to say, but again, is less influenced by individual data points, and the boundary starts to take into account kind of the overall regions of which side is red and which side is blue. So here, we have like weird shapes with k equals 1, but as k grows to say 7 and 9 and 15, okay, especially around 15, you can see this boundary seems pretty stable in that, individual data points aren't, drastically affecting it. And so you kind of have red on the right side, blue on the left-hand side. I think I've bounced up to k equal to say 21 or 31. And, by the time we're at k equal to 31, it pretty much looks almost like just like a straight line down the middle where we have red on the right and blue on the left. So, kind of my overall comments on this is that smaller values of k can end up leading to overfitting the training data, where we have kind of high variance, and you have these exclaves and enclaves formed by individual points that just ended up in kind of the opposite side, right? Okay. Whereas if you have larger values of k, they tend to, kind of over smooth the boundary region. You lose a lot of kind of local influence, which may or may not be desirable. So you end up underfitting the data a bit. Okay. So you can also, and I guess this will be our last point here, k-nearest neighbors can also be extended for regression. And the way it would work is, you still do this distance calculation, but then when you predict output for the your test case, okay, what you will do is you'll typically just kind of take the mean of the nearest neighbors. Okay, so you still do the same thing. You calculate the distance to every single point in the training data. You're going to identify the k-nearest neighbors to the your test case, but then you take the whatever numeric value you have for your output variable, and then you take the average, okay? Or perhaps a weighted average if you want to say the near points have greater influence there. Okay, so this is just a real quick introduction to k-nearest neighbors. You will have a little bit more exposure to it in your next homework assignment, where I will ask you to kind of write some code to perform k-nearest neighbors classification. And I think that's where you will really kind of learn and understand how k-nearest neighbors works. But again, it's a very simple algorithm. You just have to compute distance to every single other data point, and then using the nearest neighbors, each of those get a vote as far as classifying the new location. Okay, that's it for this lecture. Again, thanks for your flexibility in watching this online, and we'll see you next time.